diode or bipolar junction diode as a transistor, and we had seen the biasing of it in active mode under common emitter configuration, and it's working as an amplifier with the addition of the small signal input and the load resistor. And from that we had seen the formulae for current gain, voltage gain, okay, power gain, etc., the various different types of gain factors. So that is the more important part of the semiconductor and devices part of your syllabus. And apart from that, of course, the rectifier circuits and the functioning of PN junction diode as a, PN junction as a diode in both forward bias and reverse bias, and few of the different applications of PN junctions as light emitting diode, light control diode or photodiode, and also the reverse biased, reverse breakdown mode function of the Zener diode in voltage regulator circuits. So if you're clear with these type of circuit applications, you should not have any difficulty with semiconductors. In any case, you can't expect more than one question from semiconductors at JEE mains level. So it's a very low weightage topic, but yes, you need to understand the functioning of the transistor as well as the junction diode. Then we had moved on to logic gates, and it was a very simple topic, but again you have to understand the symbols for the different type of gates and how to combine the gates to execute certain type of functions like NAND, NOR, or exclusive, or etc. So please make sure you're familiar with that, particularly if you have not seen that in computer science or electronics before. And again, you can expect one question from that. So we are basically done with the syllabus. Now communication systems is one additional thing that you will need to study. And like I told you last time, I will be giving you some basic guidelines on, first of all, basic overview of communication theory, and from there, what all you need to study and keep in mind for your exam level preparation. Again, a very low weightage topic, not more than one question in the JEE mains paper can be expected. However, it is something, okay, I will look into the doubts later. So let me just, okay, so Ganesh and Shreya, I will keep some time for doubts. In fact, most of the time in class today, we can discuss some doubts and questions. But let me just start with the quick overview of communication systems. So we can complete off this portion. Yeah, just give me a moment. All right, so let's understand the basic elements of any communication system. So the broad definition of communication systems is very simple, that any process in which we are transmitting information from one point to another, that is called a communication system. So whether we are transmitting information digitally or by electromagnetic waves, or physically by sending physical documents, etc., it's all part of communication system. But here of course we are talking more in context of communication via electromagnetic radiations and electromagnetic transmission. So you can think more in context of transmitting information via electromagnetic waves, or basically radio wave transmission, that kind of situation. Okay. So it will broadly speaking, the concepts we think of over here will also apply to fiber optic communication. But uh, in a while I'll explain to you why we are thinking more in context of radio wave communication, because here our study is more about what is called analog communication systems rather than digital communication systems. Okay, so let's look at the, so think of this like a basic radio broadcast and radio communication system. So the basic elements of the communication system are three: transmitter, then the transmission channel, and the receiver. So what is happening at the transmitter level is whatever information has to be transferred, or whatever information has to be transmitted from the transmitter to the receiver, has to be converted into something that can be transmitted along the channel. So basically you have to have a transmission signal. So conversion of the input signal into a transmission signal, that is the process of the transmitter. Okay. No, Aditya, you don't need to make note for this topic. Make notes rather. I will also take you through the NCRT chapter once, the chapter PDF, and I'll mark out which sections from that you need to pay attention to. So I would suggest that you can use NCRT as the main reference for this. Okay. So yes, at the transmitter level, what happens is any input signal. So for example, the input signal could be the electrical signal coming from a microphone. So the input signal is basically the signal that comes from some transducer. What is a transducer? Transducer is a device that converts one type of information into another type of information. So example of a transducer is a microphone. A microphone converts audio waves or sound waves into electrical signals. So that's an example of a transducer. Okay. So the input signal is the signal that is coming from a transducer. Now what the transmitter does is the input signal that goes into the transmitter, it is converted into something which is called the transmission signal. So you can think of the transmitter like, for example, a radio antenna and all the other equipment that goes along with the radio antenna, which is a signal amplifier and the modulator and things like that. So inside the transmitter, we will discuss in a short while what actually happens is, see, the electrical signal that is coming from the transducer, the input signal, cannot be directly transmitted through electromagnetic waves. It has to be converted into some other form of signal, which can then be transmitted via electromagnetic waves from the radio antenna onto the transmission tower. Okay, so that process of conversion is the job of the transmitter. So what the transmitter does is it converts the input signal into a transmission signal. Okay, by a process which is called modulation. By a process which is called modulation. So we will discuss very soon about modulation in more detail. So that is the job of the transmitter. So the transmitted signal is basically the input signal converted into another form of signal via the process of modulation. And there are different types of modulations, different processes by which modulation is done. And basically you can think of modulation like the process of, basically you can think of modulation as a process of encoding information. Okay. That information is from the input signal, okay, into something called a carrier wave. So that carrier wave is basically a high frequency electromagnetic wave or signal. Okay. But that high frequency, comparatively high frequency, we'll come to the frequency ranges also, but that high frequency signal or that high frequency electromagnetic wave is now modulated by, so the process of modulation encodes information or encodes data onto it, and that becomes the transmission wave. Electrical signal. Okay. Transmission signal is an electromagnetic wave, whereas the input signal is an electrical signal. You can think of the input signal like the output coming out from a microphone. Okay, the output coming out from the microphone, typically it has to be amplified a bit, and then some other processing has to be done to it, and then the signal that you get, which would otherwise go into your speaker. Okay, if you wanted to hear that coming out of the speaker, or it would go into another transducer, which would convert it to a audio wave again or an acoustic wave again. But instead of that, what we are now doing it is we are sending into a transmitter. So what the transmitter does it is that input signal is used in a process of modulation, where the information in the input signal is used to encode information or encode data into the carrier wave. And what is the carrier wave? It is a high frequency electromagnetic wave. So now the transmission or the transmitted signal, it is basically the carrier wave which has been modulated. Understood the point? So the carrier wave, which is a high frequency electromagnetic signal or electromagnetic wave, which is what your transmission tower will be transmitting, or which is what your radio antenna will be transmitting as electromagnetic pulses and electromagnetic signals into the atmosphere around. Okay, that signal is basically what it is, a carrier wave which has been modulated using the input signal, and the job of doing that modulation is the part of the whole system which is called the transmitter. So it's a three-stage system: transmitter, transmission channel, and receiver. So the job of the transmitter is to encode the data or the information that is part of the input signal onto the carrier wave, and hence get what is called the modulated carrier wave. And that modulated carrier wave is what is going to be transmitted by the transmitter. Is it clear, Sujit? Okay. Okay. Now the transmission channel. What is the role of the transmission channel? Let's understand that next. So what the transmission channel does. Okay. So we discussed about the transmitter's function. Okay, it converts the message signal. This message signal here is the same thing as the input signal into a form which is suitable over a communication channel, and this process is called modulation. Okay, so this transmission signal, which is suitable to transmit over a communication channel, this only is nothing but the modulated carrier wave. Okay, now the communication channels function, the second part of our communication system, is the transmission channel or the communication channel. Now its function is to basically provide the channel or the pathway, okay, or the signal pathway between the transmitter's output and the receiver's input. So that output could be, I mean, that communication pathway could be in the form of, for example, ground waves, that are electromagnetic waves that propagate very close to the surface of the earth, almost on the surface of the earth, using the surface of the earth as a conducting path. Or they could be what is called sky waves. We'll discuss about this very soon, which are waves that are transmitted by the transmitter straight up into the atmosphere. Okay, and the ionosphere of the atmosphere is used as like a reflecting surface to then reflect them back to another region on the earth's surface. And that process of transmission, reflection, and then receiving at the receiver's end, that process provides the communication channel. Or in the case of modern day communication technology, you have satellite technology, where instead of the ionosphere, which is going to reflect back the communication waves or the electromagnetic waves, it is the satellites which are in orbit around the earth, which will receive the signal from the transmitter and then retransmit it to the receiver, which is at another point on the earth's surface. And that whole system in between, from transmission tower to satellite, receiving it at the satellite, and then broadcasting that signal again from the satellite's end till it is reached at the receiver's position. That whole part becomes basically the transmission channel. Okay, a fiber optic cable network is also a transmission channel. It is also a communication channel. So once, for example, your router, you can think of the router as the part of the transmitter. Like the transmitter, for example, when I'm communicating to you through this particular form of communication or this communication system, what is happening is that right from the microphone and video camera of my laptop to the operating system, the entire hardware operating system, which is converting, the audio waves which my vocal cords are generating, and the light, which represents the images that you are seeing. It is converting that first into electrical signal, then into a digital signal, which is software generated. Then it is transmitting that digital data at a continuous rate, okay, through some data transfer protocol through your modem, and that modem is transmitting that into the fiber optic communication network. So right from the camera and the microphone up to what the modem is sending into the data network, that part is the transmitter part of the communication system. And the fiber optic cable network, which is taking it from my modem to your modem, you can think of that as the transmission channel. And then your modem, which is receiving that data, then sending it into through your home's Wi-Fi router. It is coming into your computer. Then that data is decoded by your computer, and finally, after the programs run those digital files, your computer is giving it as an output as the images that you're seeing on the screen, and the sound that is coming out of the speaker of your audio system. So that whole part is the receiver's part. Okay, so from your modem right up to the output that you're getting from your output device, that part consists of the receiver part. Whereas the fiber optic network in between, that is the channel. So this is how you would interpret this, three-layer system of communication with regards to, you know, uh, communication between computers or communication via computers, digital communication via computers through a fiber optic network. But yeah, if you think of this like a radio communication system, the transmitter would be nothing but the input stage at the radio, uh, at the radio station. So whatever program is happening, if there's a live program happening, so right from the microphones and the input from the microphones going into the pre-amplifier, then all the audio processing that is happening, then it's going into the power amplifier, and that amplified uh, electrical signal is fed into the radio transmitter, which mixes that signal. And we'll understand what this mixing means. That is the term that we use, modulation actually. So it uses that input signal to modulate something called a carrier wave. Now carrier wave is a high frequency electromagnetic wave, and that modulated carrier wave, that becomes our transmission signal. So that is what the radio station's antenna is going to now transmit. And suppose we are talking about transmission via communication channel or a transmission channel, which is sky waves. So then the transmitter at the radio station's level will be sending those electromagnetic waves or transmitting those electromagnetic waves into, at a certain angle into the sky, and it will be using the ionosphere in the atmosphere as like a mirror to reflect them back to another region on the surface of the earth. And those reflected electromagnetic waves are received by the antenna at the receiver level, and those electromagnetic waves will excite the electrons at the receiver's antenna and cause those electrons to create a certain signal, an electrical signal. So basically what is happening at the transmitter stage, the reverse of that is happening at the receiver stage. So the electromagnetic waves are used to excite the receiver's circuitry into a signal, and that becomes the output signal at the receiver's end. Now the output signal is also very complicated because it is after all a modulated carrier wave. So the carrier wave has to be removed from it, and the information that was encoded into the carrier wave via the modulation process, that has to be decoded, and finally that will go into the output device. So in the case of a radio system, the output device would be the speaker of the radio system. So you would hear it as an audio signal coming out of the speaker. So that is basically the three parts. So you can visualize this three-layer system in whatever context you like in terms of communication. Okay. So So as we discussed, the receiver's function is to process the received signal. So what is going to be the received signal? It is again going to be the same thing as the transmitted signal only. Of course, the transmitted signal undergoes some changes while it is going through the transmission channel. We'll discuss about that also. But more or less, it is a modulated carrier wave. The way it was, transmitted at the transmitter's end, a similar kind of wave is received at the receiver's end, and then the appropriate data is to be recovered from that, or a proper signal has to be recovered from that, so that you get the output message or the output signal. So that is the job of the receiver. Okay. Now, before we go ahead, let's understand what all happens to the wave between the transmitter and the receiver as it's going through the transmission channel. So the important things that the wave suffers, one is noise and interference. Okay. Because what is happening, your transmission tower, it's sending electromagnetic waves, but those waves are also interfering with random electromagnetic waves from other things. Okay, like there are electrical devices, like there might be electrical thunderstorms, etc. All sorts of natural phenomena which create electromagnetic waves, which will be interfering, and by that process, adding what we call noise. Noise is another term for noise. Is not the sound sense of noise over here. Noise in a communication system is an unwanted electromagnetic wave that interferes with the transmission signal. Okay. So, for example, in the case of, you might have heard of the term jammers, radio frequency jammers. So, radio frequency jammers use high amplitude noise signals to actually, interfere with the transmission signal in such a way that the data is lost, and therefore the person trying to communicate with another person through that transmission channel will not be able to effectively communicate, because the encoded data in the form of the modulated wave, it gets too distorted because of the noise which interferes with it. Again, interference is the same kind of that we've discussed in context of waves before. It is the overlap of waves, superposition of electromagnetic waves, that processes interference. Okay. So again, this is an unwanted situation. So noise is one unwanted problem. So, and noise has the effect of creating distortion because it changes the waveform. So distortion is a term which is a change in the waveform because of the addition of noise or because of the interference with noise. Another thing which is not mentioned over here, which happens as the wave passes through the transmission channel, is signal attenuation. Okay. Signal attenuation. The term attenuation is when there is reduction of power. Okay. So signal attenuation is basically loss of power. Okay, with distance from the transmission tower, with distance from the transmitter. Okay, so a receiver over here versus a receiver over here with respect to the transmission tower, this guy will receive more power compared to this, because with distance there is loss of intensity. And loss of intensity not just because of that 1 by r square rule that we have seen earlier, that intensity from a power source is equal to power divided by 4 pi r square. So obviously intensity is proportional to 1 by r square, so there is loss of power received because of distance factor, but also because that on the way, as the electromagnetic waves are transmitting from one point to another, there is continuous interference also happening. So that also results in loss of power. So this interference with noise not only causes distortion of the signal, but it also causes power loss, and that power loss contributes to what is called attenuation. So the term attenuation is used for loss of amplitude or loss of power. Power is proportional to square of amplitude. So that also happens. So that is why for long distance transmission, as part of the transmission channel, you will have another stage called signal boosters. So from the radio station that is transmitting the original data, there will be several radio stations in between before you come to the receiver's end that will receive the signal, amplify it, and again retransmit. Then again at a certain distance, there will be another radio station which will receive the signal, amplify it. So those are called the booster stations. Okay, so they boost the attenuated signal to bring back the power back to a certain threshold level so that it can reach a destination which is far away. So all that is part of the transmission channels. Okay. Now let's come to this part. Okay. Now this is more in context of your general knowledge actually, because as I told you, in our syllabus there is nothing about digital versus analog, but when we use analog, we use a terminology called digital, which is modified with the data coming from the input wave. So it is nothing but a way of encoding data, data encoding. That is what we are talking about over here. So data encoding, before it is transmitted through a communication channel, is done by two methods: analog versus digital. So digital is when all data is converted to ones and zeros or high and low. So the method of encoding data is binary. So when we have binary data encoding and binary data transmission, that is called digital. Whereas when the data is encoded via waveforms, like you would have seen audio waves represented in audio software, etc., that is called the analog waves, or it is called analog signal. Okay. So when we use the input signal, which is basically an electrical signal, directly to modulate the carrier wave, then it is called an analog transmission signal. Whereas if the input signal coming from some device like a transducer is first converted into a digital signal, and that digital information is used to modulate that digital signal is used to modulate the carrier wave, then it becomes a digital communication system. Okay. So there are some advantages and disadvantages that I've listed out for you for digital versus analog. So the advantages include the fact that because the information is in digital, it is easier to design a system which is immune to noise, because we can encode the data in such a way that noise can easily be removed from the receiver's end. Okay, so interference, noise, okay, it offers a lot of flexibility in terms of data protection, data encoding, etc. Okay, and different type of messages such as voice, video, okay, text, etc., can can be formatted into the same transmitter. So you can use the same bandwidth of transmission of electromagnetic waves to send different types of data within the same transmission packet, because you're able to encode data in that way. Whereas in analog, you cannot do that. If you're sending an audio signal, then you have to use a certain bandwidth of the carrier waves to send that particular signal. Along with that, if you're sending a video signal, then you'll have to use a different bandwidth. Okay. And of course, as I told you, that message signals can be encrypted for security and data sensitivity, etc. Okay. But at the same time, there are disadvantages, and the biggest disadvantage is that it is very complex, and it is also costly, because you need such things as satellite channels, optical fibers, etc. These are the typical types of channels that I use: satellite channels versus optical fiber networks. So both of which create an additional expense. Okay. Analog also has a few benefits, but don't need to get into that. What we need to understand is that analog is still used till date for basic radio transmission and basic communication networks. Okay. And okay, it's a simple technology, it's a well-known technology, and it is used for broadcast systems like radio, a lot of telephone networks, okay, and a lot of internal radio communication networks, like walkie-talkie networks, etc. So in that, the kind of technology that is used for communications is analog systems. So analog is still it's basically like a dinosaur, but it still exists because of these simple advantages. And sooner or later, analog will get replaced completely by digital. But you have to understand analog technology before you can add the layer of digital onto it, because the basic process of communication, the basic model of communication is the same. It is just that before you encode the information from the input signal into the carrier wave, you convert it into a digital data protocol, or you convert it into a binary language. And because you've converted into a binary language, the output you will get at the receiver's end will also come in the form of a binary signal or in the form of a digital signal. And that makes it that much more flexible, that much more encodable, and therefore you have all those advantages that you can make it immune to noise. You can incorporate security encoding and things like that. And because you can encode it, you can encode different types of information like voice, video, etc. into the same transmission channel. So those advantages all come out because you have done that extra two layers, that at the input signal level you have converted the analog into digital first and encoded the digital data onto the carrier wave, and back at the receiver's end, the you are decoding the transmitted signal into a digital signal first. Okay, and that digital signal is being processed as your system before the final output comes out. So that extra layer of analog to digital and later digital to analog, which in engineering terms you would have heard the term A to D and D to A. This that is the extra layer that provides all the advantage, but that is the extra layer that also provides all the excess cost and excess complexity in the system. Okay, so A to D and D to A, you would have heard this term ever. So this is analog to digital and digital to analog. So a very simple example of A to D is a sound card. This is what the function of the sound card onboard your, it can be the onboard sound card in your this thing on your motherboard, or it could be an external sound card that you're using via USB or Firewire or anything. The job of the sound card, what it does is that any input analog signal, okay, whether it is coming from a microphone or another audio device, etc., it is converted to digital. Okay. So that is the job of the sound card. And at the other end of the sound card, there's also D to A happening, where the computer, after processing the sound in digital domain, the digital signal or the digital audio signal, okay, like an AAC file, okay, or a wave file, okay, or even an MP3 file, its output goes into the digital to analog converter, D to A converter, and converts it into an analog signal. So what is an analog signal? An analog signal is nothing but an electrical signal. So it's basically like an AC signal, an AC signal that mimics the actual audio amplitude. Okay, and that is then sent into the speaker cabinet, and that comes out as sound because that analog signal is used to drive the cone of the speaker back and forth via electromagnetism. Okay. So this is an example of A to D and D to A at your everyday usage level. Okay. Now let's come back to the very important part of. So this is the main aspect of our study of communication networks, okay, or communication. That is the process of modulation. This is the job of the transmitter, as I told you. So what does the transmitter do? It takes the input signal from a transducer, okay, and it takes another signal which is from a signal generator, which is called the carrier wave, okay, and it mixes these two to give the transmission signal. So what it does over here, this process is what we call modulation. So you can think of modulation as a method by which the information of the input signal is encoded onto the carrier wave. So as I told you earlier, the carrier wave is a high frequency electromagnetic wave. Okay, it is, the carrier wave is a simple high frequency sinusoidal EM wave, which is suitable for the channel's bandwidth. Okay, for the broadcasting system, which can multiplex it, etc. Okay, that is, multiplex means that different message signals can be transmitted at the same channel at the same time, and it is also suitably high frequency so that the signal noise ratio will be less. That is, it is easier to eliminate noise. So, the carrier wave is always of a frequency which is suitably high for these purposes, that it can be transmitted over a long distance. It can be used to multiplex different types of information in the same channel, and it suits the given channel's bandwidth as per the user's requirement. And it's therefore also easier to reduce the amount of noise compared to the amplitude of the noise compared to the signal levels noise. Okay. So modulation is the process by which we use the input signal to modulate or to modify or to encode data into the carrier wave. Okay. So let's see next how this can be done. So this is typically done. Now remember, we are talking about analog mostly. Okay, we're not talking about digital over here. Digital techniques are a little bit more complex than this. Okay. So there are three main methods by which we can do modulation. Okay, so a carrier wave has three independent parameters. Like any sinusoidal wave, it has three parameters, which are amplitude of the wave, the phase, and the frequency. So information from the input signal can be used to modify any one of these three, either the amplitude or the phase or the frequency. So when we use the information from the input wave to modify the amplitude of the carrier wave, then it is called amplitude modulation, AM. Okay, and this is the one we are going to study in little bit detail over here. When we use the information from the input wave or the input signal to modulate the frequency or to modify the frequency, it is called frequency modulation. And when it is used to modify the phase, it is called phase modulation. Okay, so if you think of the carrier wave as something like this, it is some kind of signal. Okay, so it has some kind of amplitude into some kind of frequency, some kind of phase. So here AC is the amplitude of the carrier wave. Okay. Omega C, which is 2 pi FC. FC is the frequency of the carrier wave. Okay. And phi is the phase of the carrier wave, the phase constant of the phase. Okay. So without any modulation, our carrier wave just looks like a normal high frequency sine wave, something like this. I mean, my drawing is not good, but this should be uniform in amplitude and they should be uniform in time or in frequency. Okay. So that is an unmodulated wave. But if we use the input from the signal, the input signal to modify the amplitude, then we will get something, we'll get a carrier wave where the amplitude itself is getting modified. So we'll get a carrier wave which after amplitude modulation might look something like this. So this is amplitude modulated. Okay. If we use the input signal to modify the frequency, then we will get a frequency modulated wave which might look like this, that at places will have uniform amplitude, but at places its frequency is high, and at places its frequency is changed, then again its frequency is changed. So it's not having uniform frequency because the frequency is getting modified or modulated using the information from the input signal. And likewise, phase is a little difficult to draw but phase modulation is difficult to represent geometrically. But this phase constant term, if we change this or we modify this or continuously modify, that is the term used for modulation. So if this term is getting modulated by the input signal, then the process is called phase modulation. So as I said, we will discuss at our syllabus level only one of these in reasonable detail, which is the amplitude modulation term. We'll discuss about that next. So let's both visualize as well as understand mathematically what is the meaning of amplitude modulation. So this is an example diagram of a high frequency carrier wave, something that I was trying to make earlier. So it has uniform frequency, uniform amplitude. Okay, like this. Okay. Now let's say the input signal is the signal coming from a simple sine wave generator. So it is not really the signal coming from a microphone, which has a complex combination of frequencies. But let's simplify things and say that the input message is simply the signal that is coming from a simple sine wave oscillator. So it's a sine wave of much lower frequency, as you can see. It has larger time period compared to the carrier wave and much lower frequency therefore. Okay. Now if we use this wave, okay, that is the input wave, low frequency signal, which is the input signal. If we use this to modulate the amplitude of this one, that means this one's vertical, this thing, the amplitude is modulated. That means it is continuously being modified using this signal. We will get this kind of a modulated amplitude signal. We'll get an amplitude modulated signal, which will now become the transmission signal. So this is the signal that the transmitter will broadcast through the communication channel. And finally, this is the signal after some attenuation and re-amplification and all that. Some signal of this type only will be received at the receiver's end. Okay. So now let's understand the process of amplitude modulation in terms of theory. Now you don't really need to get into detail with the equations, but I'm just explaining to you over here so that it doesn't seem like all just theory alone. So for amplitude modulation, okay, there are 4 steps basically. The carrier signal, which we talked about earlier, carrier wave. This is generated by something called the wave generator. So this is your high frequency sine wave. Okay. Then you need the modulating signal. The modulating signal is nothing but the input signal that we were talking about earlier. So you can think of the input signal like a low frequency signal. Okay. Now for demonstration purpose, I had shown that low frequency signal as a perfect sine wave, but typically it will not be a perfect sine wave. It will be a combination of different type of waveforms. So it might be something like this. Okay, but its variation is much slower compared to the carrier wave, which will be a strict sine wave of very high frequency in comparison. So a carrier wave will be like this, whereas the input wave or the input signal could be any sort of information, but varying much less rapidly compared to the carrier wave. Okay, so the overall modulated signal, how we will get that? Let's understand this. Okay, so don't worry about this 4th term and this 3rd term. I'm coming to that. Let's see how this process happens. So let's think of it in a very simple context that we have. So in an actual system, it is somewhat more complicated. Okay. So we have our carrier wave function. This is called vice versa. It's the same thing actually. Yeah. So this is our carrier wave function. It has some kind of amplitude, which is capital C, and it has some kind of angular frequency, which is omega C. Okay. So the frequency of the carrier wave in hertz is this much. And typically this will be high frequency in megahertz range and all that. And this is the carrier wave amplitude. Whereas the modulating signal is this one. The modulating signal, for simplicity, I'm again taking it as a sine wave, but of much lower frequency. So this omega m will have a frequency which is much smaller compared to the carrier wave's frequency. Okay, and capital M here is the amplitude of the modulating signal or the input signal. So remember what we mean by the modulating signal is the input signal. Okay, so how we'll get the modulated signal now? We will get the modulated signal in such a way that the carrier wave was like this. It was some amplitude into sine of its own frequency plus this thing. Now what is happening when we modulate it? This term, this amplitude will be modulated, okay, by the input signal or the input wave, which is nothing but the modulating wave. So what is the modulating wave going to affect? The modulating wave is going to affect this amplitude. So our modulating wave was capital M sine omega mt plus some phi. Okay, where this was the amplitude and this was the frequency of the modulating wave. So now we can see that this thing gets affected by that. Okay, so the modulated signal finally, or the transmission signal, which is the modulated signal YT, will be given by this kind of factor, that it will have some amplitude plus the modulating signal ym into the carrier wave. So that in my language is YC. Second come type twice. Okay. So when you substitute in the formula here, you can see that this whole thing is getting multiplied by a term which is modulated by this wave, the modulating wave. This is our modulating wave. So this becomes capital A plus M sine omega mt plus phi m. Okay. Whole thing multiplied with C sine omega ct plus phi c, where this is the high frequency term and this is the comparatively low frequency term. Okay. So this is this entire term here. This term here. Okay. Now the rest of it is simple trigonometry. So the way to interpret this becomes, the way to interpret this, which we are getting by amplitude modulation, is open this bracket, okay, and make use of this formula, that sine omega m t, okay, into sine omega ct. So sine A sine B formula, and this has that formula 2 sine A plus B by 2, that particular term. So that formula is used over here. Okay. So that is how this is getting expanded into this. So ultimately we get a waveform which is like the superposition of three waves. We get a waveform which is this. Yeah. So I'll just magnify this a bit. So this equation that you see here, this is coming from the expansion of this. Okay. So ultimately you can see that the transmitted wave, if it consisted of something this simple, that the carrier wave was a single sine wave of frequency omega c, and the modulating wave was also a simple sine wave of frequency omega m, then the transmitted wave will consist of this sum of three frequencies: omega c, okay, omega c plus omega m, and omega c minus omega m. So what happens is that modulating your carrier wave with a simple sine wave of frequency omega m, of angular frequency omega m, it creates what we call two sidebands. Along with the carrier wave frequency, there is an upper sideband frequency of omega c plus omega m, and there is a lower sideband frequency of omega c minus omega m. So if this method of transmission is going to be successful, then our data transmission channel or our broadcast channel should have this kind of bandwidth. It can support the frequencies in between the lower sideband and the upper sideband. Okay. So, for example, this is giving us a graphical picture of, let's say, the carrier wave has a frequency in megahertz. Okay, but the modulating signal was 1 kilohertz. So the upper sideband will be whatever this carrier frequency was plus 1 kilohertz, and the lower sideband will be whatever frequency this was in megahertz minus 1 kilohertz. So from the lower sideband to upper sideband, we need a bandwidth of 2 kilohertz, whereas the center one is the actual carrier frequency. Okay, so this is the concept of this is the basic concept of amplitude modulation, as I explained at a very simple level, okay, where we are just looking at a single sine wave used to modulate, single sine wave used as a modulating signal to modulate a high frequency sine wave carrier wave. Okay. Now, with the basic concept of modulation and the resultant sidebands, the same principle can be applied to more complicated systems of modulation using speech, music, and other sounds. So the difference will be, while your carrier wave will still be the same kind of wave, a sine wave of high frequency, but your modulating wave will become more complex. It will not be a simple sine wave. So it will be a combination of sine waves, that Fourier analysis kind of situation. So so that basically when they say theory can be used to break down the sound into a series of sinusoidal signals, they're talking about Fourier analysis here. So any complex kind of modulating wave also can be broken down into a sum or a series of summation of sinusoidal signals. So there'll be multiple modulating frequencies, whereas there'll be a single carrier frequency. So there'll be an entire upper sideband and an entire lower sideband, which will consist of the carrier frequency plus the entire range of frequencies present in the modulating signal. The lower sideband will consist of the carrier frequency minus the entire range of frequencies in the modulating signals. So that is why an entire bandwidth is required to transmit and receive that particular amplitude modulated signal. Okay. So this is in a nutshell what you need to know about uh, communication systems, because in detail you have only amplitude modulation. So in terms of formula, you just need to remember this important thing, that if your carrier wave frequency is omega c, so if you took an actual example, suppose your carrier wave frequency was, let's say, 12 megahertz. So that means it is 12 into 10 raised power 6 hertz. So your omega c is 2 pi fc. And suppose you're talking about a modulating wave, which is like an audio frequency. So it's typically something like, let's say, 2 kilohertz or 2 into 10 raised power. Sorry, this is modulating. I'll correct that. So this is 2 into 10 raised power 3 hertz. Okay. So this is our modulating frequency. And this is our carrier waves frequency. So this would be 2 pi fm. So you just need to know this formula. The lower sideband and the upper sideband for the amplitude modulated signal. If you're doing amplitude modulation of the transmission signal, the lower sideband will have let's say F1 of this, and the upper one will have F2 of this. It's really this simple. This is all you need to know in terms of formula. Okay, convert it to omega by multiplying by 2 pi. Okay. So this is the basic idea. Now I'll just take you through the NCERT PDF once and give you an idea of some of the things you can go through and read, so that it's easier for you to keep this in mind, and also it will help you more at the board level. Okay. So I'll just take you through the basics of this. Just a minute. Right. So let's just do a quick overview of the chapter which is here. So this is a basic introduction. You just need to go through this section once. Yeah. Elements of the communication system. Let's come to that. Again, this is some historical data. You don't really need to go through this in detail. Yeah. So elements of the communication system, what we understood earlier also, same thing. So basically it's a 3-element system: transmitter, the channel, and the receiver. So information source, it converts into message signal, or what we call the input signal. Okay. And what the transmitter does is it combines the carrier wave along with the input signal into the transmitted signal, and the transmitted signal is nothing but the modulated carrier wave. Okay. And that modulated carrier wave can be amplitude modulated, phase modulated, or frequency modulated. 3 different methods. And then the receiver, addition of noise, all these things. Now where NCERT goes into a bit of more detail, which you will not need from your JEE point of view, but you will require from your board point of view, is first of all, a lot of different terms are defined and you should understand these terms. So for example, transducer, I told you about transducer also. It converts one type of information into another, or one type of energy into another. So electrical transducer may be a device that converts some kind of physical variable like pressure or sound pressure level or temperature or something like that into a corresponding electrical current or electrical signal. So that kind of thing is a transducer. But in reality, even the reverse is a transducer, something that converts an electrical signal into a physical variable. That is also a transducer. So just like a microphone is a transducer, a speaker is also a transducer. An electronic thermometer is a transducer. But electric heater also in a sense is a transducer because it converts an electrical current into heat energy. So in the broader sense of transducer, that is there. Okay. Then signal, okay, we've discussed about. Okay. Now few more technical terms: noise, transmitter, receiver, attenuation. So these are the terms that you should be familiar with, especially for your board level questions and all. What is noise? What is transmitter? What is receiver? What is attenuation? Loss of signal strength. So technically, basically, it's loss of power, but here they've just defined it as loss of signal strength. So these are some of the definitions and things you need to know. Okay. Amplification. Now you understand amplification very well because we just discussed about amplifier before. But why do we need amplification within a transmission channel? Because there is attenuation. So it is necessary to compensate for the attenuation of the signal that happens as part of the communication channel. Okay. And of course, we have discussed about, for example, bipolar junction transistor as an amplifier. So there we understood that it is a active device, active 3-pin device. So it requires power source. So DC power source is there. Even if we use AC power to power it, internally the amplifier has rectifier circuits which converts that AC into DC. So always we require DC power source for an amplifier. Anyway, so as the signal strength becomes weaker, it can be amplified to the required strength using the amplifier. So that is the job of the amplification part of the system. Range is just a definition we use for the distance from the source, that is the transmitter, to the destination, which is nothing but the receiver, such that you can receive it at full strength. Okay. Bandwidth refers to the range of frequencies of the transmission channel. Okay. So technically this bandwidth is actually the range of frequencies or band of frequencies of the transmission channel. That is, your transmitted signals have to be in a certain bandwidth of frequency. So that is called the communication systems bandwidth. Okay. Modulation, you already understood. It is the modification of the carrier wave via amplitude modulation, frequency modulation, or uh, phase modulation. Demodulation is the reverse of that, which happens at the receiver's end. Okay. A signal repeater is basically something that receives, amplifies, and retransmits. So it's a signal repeater. So repeater can be used to increase the range of transmission, as you can see. So each of these towers is doing the job of a signal repeater. Whereas at the top of the mountain, you might have the transmitter, or you might have the transmitter here and the receiver here. In between, you have all the repeaters. Okay. Now they've also given some sort of general idea of the bandwidths in traditional systems. Okay. So for example, speech, human speech, the range of frequencies from about 300 to 3.1 kilohertz. So the difference between these two you can see is 2800 hertz. So any system that we are using to transmit waves which represent human speech, or waves that are used to encode human speech, that must have a frequency bandwidth of at least this much. Otherwise, some part of the voice signal will not get transmitted. Okay. For music and proper audio, it's at least 20 kilohertz because the frequency range is much wider. Okay. For video signals, the transmissions of pictures require about 4.2 megahertz of uh, bandwidth. Okay. And when you combine audio and video, you require about 6 megahertz of bandwidth for transmission. So these are some general things that you should know typically more at your board level. These. Now, this is a diagram where they are considering only analog signals, and they are superimposing sinusoidal waves of a series of frequencies, f02, f03, f0, like this. So the more the number of frequencies you add, like if your number of frequencies is only one, you see there is a simple sine curve. Now, if you add sine omega t with sine 2 omega t, you get a slightly more complex kind of curve, which will be like this one, the one which is represented by C. Then you add two more. So like that, the more the number of harmonic terms you add, the more the complex the resultant wave becomes. And if you add infinite number of them, it becomes something like a square wave. Okay, so this is a basic explanation of Fourier analysis which they are showing in the case of addition of harmonic terms of sine. Okay, so this is not really required for you. Okay, now bandwidths of different transmission medium. So again, here there is some data for you. The typical transmission systems, what kind of bandwidths they require. Okay, coaxial cable is used, which has a bandwidth of about 750 megahertz. Okay, and for that the carrier frequency is typically less than 18 gigahertz. Okay, whereas space waves, which are basically radio waves, there the range has to be several hundred kilometers. Okay, and the frequency range has to be a few gigahertz, because a lot of data is being transmitted through different channels, therefore. Okay, and therefore, you know, this entire frequency range of few gigahertz, it is broken and subdivided into more segments. Okay, whereas optical communication systems, they require this kind of frequency range of, you know, terahertz region. And then they talk about spectrum allocation is done by, you know, international bodies and all that. So this is some important for, you know, ranges for wireless communication. For example, cellular mobile communication happens at this kind of frequencies range. Okay, so this frequency band is basically from the lower sideband to the upper sideband. So you can understand that the carrier wave frequencies will be in this kind of range, the average kind of range. So you can see satellite communication, very high frequency. Okay. Now another important section is the different types of electromagnetic waves that are used in communication systems, or, you know, different types of channels of electromagnetic waves. So the first is ground waves. So when you have a system where high frequency carrier waves or modulated carrier waves are transmitted through the ground. Okay, so basically in such a case, the antennas have to be located very close to the ground, on or very close to the ground, and they have to have very large physical size. Okay, because this thing is again important, that the wavelength of such a wave, suppose that is lambda, then the size of the antenna has to be of the order of lambda by 4 for the ground wave transmission. So a couple of more important points you should know about the ground waves. Okay, this mode of propagation is also called surface wave propagation, and the wave glides over the surface of the earth. So it basically uses the surface of the earth as a wave guide, and it induces current on the ground, and through that current only the signal is transmitted. So that is why these are called ground waves. Okay, and the maximum range of coverage depends on the transmitted power and frequency of less than few megahertz. Carrier wave is used for that. Okay. Then they've given you a table of the different layers of the atmosphere. Okay, for which, for us, of course, the important thing here is going to be that fact that the ionosphere is going to act like a reflecting layer of the atmosphere when it comes to sky waves. So after ground waves, the second kind of transmission channel that can be used is the channel through sky waves. So in sky waves, what is happening is that the transmitted waves are of this kind of frequency of megahertz range, 30 to 40, and long distance can be achieved by this because the ionosphere will be used as a reflecting medium. So this is the frequency range. It's a long distance communication because the ionosphere, okay, it reflects the radio waves back towards the earth. So this mode is called the sky wave propagation, and it extends from a height of about 65 kilometers to about 400 kilometers above the earth's surface. Okay. And this ionization occurs due to absorption of ultra UV radiation, etc. All these things you can go through. Okay. So they've also given you a, so the ionosphere acts as a reflective layer for certain range of frequencies, 30 to 30 megahertz frequency. Higher than 30 megahertz frequencies, they penetrate the ionosphere and escape. Okay. So that is like, I mean, typically we don't go beyond 40 megahertz. It's 30 to 40 megahertz, the range. So this is a diagrammatic representation of the sky wave phenomenon. So this is your transmitter, and this is the reflection happening at the ionosphere. Okay, and here should be your receiver. So this entire process, this is the channel, the communication channel. Okay. Now you also have the third type of EM waves for transmission, which is the direct space waves. So space waves doesn't typically mean through, outer space, it's through the atmosphere only. But when there is direct transmission of electromagnetic wave from the transmitter to the receiver, so when that is happening, you are limited by the fact that the Earth is spherical in shape, and therefore to have a large range, you need to really create a tall antenna. The taller the height of this antenna will be, the longer the range of this will be. Okay. So they've given you the formula of that tangent thing, that this formula, where it comes from, I'll show you. So imagine this is the surface of the Earth. Now if your transmitter tower is at a height h, okay, then the maximum range it will cover, you need to draw a tangent from here. That will tell you the maximum range it will cover. Okay, so this distance will tell you the range it will cover. So this formula is coming from that kind of calculation. So again, at board level, all this will become important for you. Okay. Now, finally, there is the satellite communication, okay, which goes to a very complex system where the transmitted wave is received by the satellite actually, and it's not directly reflected back. It is more like it is first amplified and then reflected back. But anyway, here you're taking a simple picture of it. Okay. Okay. Then you can go through this section which talks about the necessity for modulating, which we discussed earlier. Okay. Okay. There are all these factors which need to be taken into account, which decide the carrier frequency range, the size of the antenna you're using, the effective power radiated by the antenna, the range of your system, the what we call multiplexing or mixing of signals of different transmitters. All these factors together will determine the kind of frequencies that are used for carrier waves. And these all point to the fact that carrier waves need to be of comparatively high frequency. So this is your carrier wave equation, which we were talking about earlier. This is the equation of the carrier wave. Now this carrier wave will be mixed or will be modulated by the modulating wave, and that will form the transmission wave. So again, as I said, at our syllabus level, so if this is the carrier wave and this second one is the modulating wave, then amplitude modulation will look like this third picture. So as you can see, this is the carrier wave, which is of high frequency. And as an example, they've again taken the modulating wave or the input signal as a low frequency sine wave. But in reality, typically it's a more complex wave, which is a combination of sine waves. So if you do amplitude modulation, this is how the transmitted wave will look like. This will be the transmitted wave. You do frequency modulation, you can see that this factor is modulating the frequency. So wherever this is having a high value, the frequencies become high. Wherever this is having a low value, the frequencies become low. So the frequency of the carrier wave is getting modulated by the value of the modulating wave. So this is your frequency modulation. And phase modulation is, as I told you, it's a little difficult to visualize, but if we program it and make the output, so in the carrier wave, the phase factor is getting modulated by the uh, modulating wave or the input signal. So these are the different types of modulations. Okay. And finally, that same mathematics of the amplitude modulation, which we had talked about earlier. So this term here should have a bracket. I've taken this common from here. Okay. Now this term will be, we'll use the sin A sin B formula. Okay. So that will give us those terms of sin A plus B by 2 and sin A minus B by 2. And that's how the sideband frequencies will come into the picture. So when you expand that term using trigonometry, you see that the transmitted wave, which is the modified carrier wave, it has the original carrier wave frequency, and it has a lower sideband and it has an upper sideband. So along with the carrier frequency, it has the upper sideband and it has the lower sideband. So generally questions are asked just about this, the values of the upper sideband and the lower sideband. So this type of questions. Okay. And then they've given you a typical, schematic diagram of a more complex amplitude modulation, where you have something called a square, a function squarer. So basically, it's an electrical device where you input a certain signal, and it gives you an output which consists of a linear function of that signal. So, for example, if your xt is a sine function, then your output pi t here will be some coefficient into sine plus some coefficient into sine square of x, like that. Okay. And then it passes through something called a band pass filter and things like this. So this you need not go through, this is kind of optional, but this is a more complex sort of situation of modulation where we are using signal squarers also as part of the modulation process. So it gives you a more complex uh, transmission signal which has more information and more number of terms. Okay. And then finally, at the receiver's level, what happens? The received signal, it goes through an amplifiers, it goes through a detection stage, which is the IF stage. Okay. And finally, the output signal is received this way. So for example, an amplitude modulated wave will first go through a rectifier. So it will become like this. Then it will go through what is called an envelope detector. So the envelope detector detects only the envelope of the amplitude. It removes the carrier frequency. So ultimately you can see the modulating signal that we had got at the input stage, which we used to to modulate the carrier wave. That signal is what we are getting after you pass it through the envelope detector. So, these things, these kind of devices like envelope detectors and all that, they are basically multi-stage devices using semiconductor technology or solid state technology or even vacuum tube technology before semiconductors had come in. These are some of the things that you study at the basics of electrical engineering level later. So that is why all this will be a bit like, general knowledge as of now for you, because you don't really understand what's happening inside this device. But anyhow, give this a reading. So this is all about your communication systems. Okay, so if you just keep in mind the few things that we've discussed about, the three parts of the system, the transmitter, the transmission channel, and the uh, receiver, and the process of modulation. Okay, and the particular mathematics of the amplitude modulation. Okay, so how the carrier wave and the modulating wave or the input signal are combined. In the case of course, the input signal being a very simple sine wave, so you get this. So the transmitted wave can then be broken into the sum of three frequencies: the direct carrier frequency, the upper sideband, and the lower sideband, which are basically FC plus FM and FC minus FM. So that's basically what you need to know at the JE advanced level. Okay, so with that, we complete the portion of communication systems. So we'll take a short break. Thanks for attending. And after that, I'll discuss some questions and any doubts and things you have. Otherwise, we'll also discuss some questions in modern physics as revision. Yeah, so Ganesh and uh, Shreya, I think you mentioned that you had sent me some question on WhatsApp. If you don't mind, can you just send me a message on WhatsApp again? Because I have so many messages, it will be difficult for me to find it. I will immediately after the break, I will discuss those questions with you. So Ganesh and Shreya, if you can just send me a message, just an arbitrary message, so I'll be able to locate your doubts. Okay, so let's resume, people. So I'll start with a couple of doubts I have received from Shreya and Ganesh. Then I'll move on to some more doubts which you have sent. Okay, so Shreya, this one I'll help you with the ray diagram. So you have a combination of a concave mirror and a convex mirror, and you want the image to coincide with the object. Okay. So let's say the object is a source of light over here. So one possibility is that the incident rays they follow this kind of a path. They incident on the convex mirror and then on the concave mirror such that they make normal incidence. So these rays which are incident here, they appear to be coming from this point, which is the center of curvature of mirror A. This is mirror A and this is mirror B. Then they will retrace their path, and finally they'll retrace their path here also. So that's one possibility. Is this clear, beta? Okay. Shreya, I hope this is clear. Achha, this wasn't your doubt. Sorry, sir. Somebody else then. Okay. Then another possibility, I'll come back to your doubts here. Another possibility is that this is what is happening, that these rays after reflection, they converge to this point. Now this second possibility is also very easy to calculate, because what you can do is you can apply the reversal concept over here. If you apply the ray reversal concept here, then these rays incident here should give you a virtual object over here, which give you the final image coinciding with the original object. Okay, so this was one of the questions I received as a doubt for the ray diagram. So I just made the ray diagram for you. Okay. Yeah, Shreya, I think I've got your question now. Neutron collides with a stationary helium atom in the ground state. Is this the question you're asking, Peter? This question number 3 is yours. A neutron collides with a stationary helium. No, okay. Can you please send me the message again, Peter? Okay. Yeah, okay. I got it. Yeah, Ganesh, I'm coming to yours. Immediately after that, I'm coming to this. I've got your message. Next will be yours only. So this question is like this, that a nuclide collides, sorry, initially at rest, undergoes an alpha decay according to this. So this is basically some isotope of uranium, which is going to become 228 Z plus alpha. Now alpha particle, you know, is this helium nucleus. So this E will become equal to 228 plus 4. So in 32, and this Z will become 92 minus 2 on 90. So this is your nuclear reaction. Now it is said that the alpha particle produced, this alpha particle, it is found to move in a circular track of radius. It moves in uniform circular motion of radius 0.11 meter when put in a magnetic field of strength or intensity 3 Tesla. So we have to find the binding energy per nucleon of the daughter nucleus. So binding energy per nucleon of Y we have to find out. Okay. So basically, see, from this now, we will get the kinetic energy of the alpha particle. So the alpha particle, its mass is approximately 4 atomic mass units. Okay. So let's write that as M1. So X was at rest, and when it undergoes this disintegration, this alpha decay, the alpha particle is of mass M1, it goes at some speed V1. This is of mass M2, it goes at some speed V2. Okay, so now M1 V1, we will get this value from this charge particle. Okay, so the momentum of the particle, this one, will become 2EB multiplied by the radius. So that is 3 Tesla multiplied by 0.11. This will be the momentum of each of these. Okay, Shreya, so understood where this is coming from, the momentum conservation. The initial momentum of the system is 0 because it is given to you that the nuclide X was at rest. So after it undergoes this reaction, okay, so the alpha particle that is created, that will have this kind of a linear momentum, and equal and opposite linear momentum the particle Y will have. Right, so hope this is clear. Okay, now next thing, from this we want to calculate what? We want to calculate the binding energy per nucleon of the daughter nucleus Y. So but why do we need this information for binding energy, the daughter nucleus? Achha, because alpha's mass is not given to us now. Alpha particle's mass is not given to us. No, that's also given. X's mass is not given. Right. Okay. So we will have to use this to first find the Q value. The Q value of the reaction will be half M1 V1 square plus half M2 V2 square. Yeah, we can find out. So I'm telling you how this is. Okay. So this will be P square by 2M1 plus p square by 2m2. So that p you already found out here. So it's p square by 2 into 1 by m1. Now m1 is the mass of the alpha particle. So this plus 1 by m2, which is the mass of the y particle, this. Okay. So you can find out the Q value of the reaction from this. Now this Q value of the reaction is also going to be the mass defect. So that is m of x minus mass of y plus mass of alpha particle into c square. So understood, na Shreya? First you got this linear momentum. Okay, you will get this in SI unit over here. Whatever we get, 3 into 2 into 1.6 into 0.11 into 10 raised power minus 19. This linear momentum is in kilogram meter per second. Okay. So substitute this here, take this mass in kgs and all that. So you will get this energy in joules. Then divided by one electronic charge, so you convert it to Q value in electron volts. So that it's easy to handle. Now you compare with this equation. And don't forget about, don't worry about the explanation. Just listen to what I'm saying here. So see, you have got the uh, momentum of the alpha particle, that is from the circular motion part, right? This much is clear. Okay. Now once you got the momentum, from that you know the momentum of the daughter nucleus y is also the same in magnitude because it's equal and opposite in direction. So I know this linear momentum p of both of them. So the kinetic energy of the products is basically what? P square by 2m1 plus p square by 2m2. And m1 and m2 are nothing but the masses of the alpha particle and the mass of the daughter nucleus, both of which are given to you. So you can calculate the Q value in joules and then convert it to electron volts. Right, so that is also clear. Now equate the Q value with the formula in terms of mass defect. Okay, so you have calculated the Q value here, substitute this here, and this is unknown, these two are known, so you get mx. We get mx. So once you know mx, from that you will get the binding energy. The binding energy for x will be equal to, it had what, 230, sorry, it had 92 protons and 232 minus 92, so that's how much. So basically mass of constituents minus mass of x. Okay, so you find out mx here and now you substitute in this formula. नहीं कैसे बेटा, क्योंकि Q वैल्यू नहीं पता ना अपने को. We don't know the Q value of the reaction, it is not given. So we calculated the Q value from the information about momentum and from that kinetic energy. Okay, then we substitute. Okay, so now this binding energy of X will be equal to 92 times mass of proton plus, how much is it? 232 minus 92. So कितना हो जाएगा? 160. No, sorry, 140. Yeah, 140 mass of neutron minus mx into c square. So from that we'll know binding energy, and then we'll know binding energy per nucleon as whatever this binding energy of x is divided by number of nucleons. So that is, is this clear now? The process is clear, beta? Shreya, is the method clear now? Okay, next, Ganesh, I'm coming to your doubt. For y, na? Acha. Oh, we need to find binding energy per nucleon for y. Then all this was not required. Then so you already have the mass of y, na? and mass of proton and neutron are given to you in that question here. Then all these things were not required. Might be some error in the question, because unnecessarily why all this information has to be given there. Mass of neutron, proton and Y is given. Okay. So you can just check once, it might be a misprint. It should be the binding energy of X, because that is the unknown quantity. Binding energy per nucleon of X you check, because otherwise the question doesn't make sense. All this information about Q value and all that is not required, na, then. Yeah, so binding energy ऐसे calculate किया ना, 90 protons, 138 neutrons minus the given mass into C squared divided by total number of nucleons. That's fine. Then according to what they've asked, the solution is also correct. But then the question doesn't make sense. Now, why give all this information and all you need to find is the simple binding energy of Y? So I think the question must have meant to ask binding energy of X, for which you first need to calculate mx. Otherwise, it's just a direct formula. Okay, Ganesh, I'm coming to your question now. This is a mechanics question. Thin plate of mass m affixed on the upper end of a spring, lower end of which is affixed on the ground. In equilibrium, the spring is compressed by an amount x naught. Okay. So we have this situation first. And this is in equilibrium initially. So we know that kx naught is equal to mg. Now what is happening is another plate is dropped. Another thin plate of mass 2m is dropped from a height 3x naught above the plate A, hits the plate A, moves downwards together with the plate A. Okay, so the second plate B. So this is at rest, this is in equilibrium. This is at rest initially, but starts falling with G. So it has a mass 3m. Now it is dropped from a height of 3x naught. Okay, and thereafter what is happening? Both the plates rebound upwards. What maximum height above the initial position of plate A will the plate B rise? Okay. So for this you need to understand first of all, Ganesh, that when plate B collides with A, after the impact, what will be the system's momentum, what will be the system's energy? This thing we need to calculate. So just before impact, this is 0 and this is or root 6g x naught. Okay, so just after impact, they will have a combined velocity of how much? They'll have a combined velocity of 3mv divided by 4m. So 3/4 of root 6 gx naught. Okay, so from this point onwards till they lose contact, and even after they lose contact actually, or 2m, sorry. So this one is having mass 2m. Right. So this will become 2/3. Okay. Anyhow, okay. So this system now has a total energy of half into m plus 2m, that is 3m, into 2/3 root 6 gx naught whole square. Okay, plus some sort of gravitational potential energy. Let's write that as u naught. This is gravitational potential energy. So this term will become half 3m into this. And we had kx naught is equal to mg. So you can write this as 9 by 2 mg x naught. Okay, plus u naught. This is the total mechanical energy of the system. Okay. Now, when will they separate? They will separate when the spring comes back to natural length. So from here, the system is going down to some maximum compression. That time the V will become 0 for both A and B. And then it will come back to a situation where A and B are still together. So they are having common velocity, but the spring is back to natural length. Okay, so this is when they are having a common velocity of V prime. And after this, what will happen? After this, A's motion will be retarded with greater than G because the spring will get extended, whereas B's motion will be retarded with G. So they will have different velocities. So now VB starts becoming greater than V. Okay, but to find the maximum height to which B goes, we just need to find V prime. Okay. Because later at some stage, B goes somewhere here and stops. So from this point, this maximum height to which B goes is V prime square by 2G. So we just need to find this V prime. Are we clear up to this point, Ganesh? Okay. So now you compare this picture with this picture. Okay. So here in comparison, the kinetic energy of the system is half 3m V prime square. The elastic potential energy of the spring is 0. And the gravitational potential energy is u naught plus 3m g into how much it has climbed through compared to this. Here there was a compression of x naught, here is at natural length, so just x naught. Okay. So now equate this energy with this energy. So we have 9 by 2 mg x naught should be equal to 3 by 2 mv prime square plus 3 mg x naught. Should be 9 9 by 2 minus 3. So that's how much now? 3 by 2. So this is what I'm getting. I'm getting V prime as root G x naught. So that means that maximum height it will climb from there will be by 2. Okay. But they're asking from initial position of A. So from initial position of A, delta H for B will be that HB plus x naught. So it should be 3x naught by 2. Because the initial position of A was compression of x naught. Alright. So I don't know which step you might have made a mistake, Ganesh, but just check your calculations. Okay, Ganesh, your other question I'll come back to because it's a mechanics question and I have some doubts from this thing, modern physics, which I want to discuss in class here today. So I will come back to your other question. Now that it is there, the top of my list, I will send you some. Okay. Now I'm coming to some of the text messages I have received here. Some of you have sent me doubts from HC Verma and stuff, I think. Yeah, so Aditya, I will come to some of your doubts. So HC Verma photoelectric effect chapter, question number 10 and 11. Let's look at this. So I'll try to finish off the modern physics doubts first. Then I will come back to doubts from other chapters. Anyway, we have one more lecture this week, I think. So from now on, we have enough time for discussion of doubts. So let's come to photoelectric effect chapter of HC Verma. Okay, question number 5B. How many photons are there in each cubic meter near the Earth's surface at any instant? Okay. So this question, Aditya, we have to do with some assumptions. I'll explain. So the Earth's surface receives, so let's say this is the Earth's surface, it receives a photon flux. So it receives sunlight of intensity given to us as 1.4 into 10 raised power 3 watts per meter square. This is HC Verma photoelectric effect. Question number 5, part B that we are discussing. Right. Now it is also given that the average wavelength, assume that the light is monochromatic, which is obviously not true, but in this question we are assuming that. So the wavelength of light is given to us as 400 nanometers. So the energy of the photon, hc by lambda, we can calculate by that approximate value. So 1242 divided by 400 electron volts. Okay. So this is the energy of the photon, this is the intensity. Okay, and no light is absorbed in between the sun and the Earth's surface. Distance between the sun and Earth is so much. Number of photons falling per second on each square meter of the Earth's surface directly below the sun. That we have calculated. How many photons are there in each cubic meter near the Earth's surface at any instant? Okay. So for this, you have to understand that, Aditya, if you're talking about a small cubic volume, I mean small volume near the Earth's surface, where that volume is 1 meter cube. So at any instant, how many photons are present in that volume? You understood the meaning of this question, the B part. It's saying how many photons are present in 1 meter cube space or volume near the Earth's surface at any instant. Okay, so have you understood the meaning of the question, Aditya? Okay, I'll explain. Okay. So now let's say that we are thinking like we are standing on the Earth's surface, so it appears horizontal like this, and there is a flux of photons which is falling vertically towards the Earth's surface like this. So you can think of these photons like particles which are traveling with a speed, which is the speed of light. Okay. Now, if you take a surface area of 1 meter square, okay, then you already calculated the number of photons that passes through this. Okay, so the photon flux, that is number of photons per second per meter square surface area that are falling, that you already calculated. So let's say that photon flux is n, that is equal to what? It is the intensity divided by the energy of the photon. So it is 1.4 into 10 raised by 3 divided by 3.105, but so get multiplied with this to get number of photons per second. So this is the A part. You already calculated this, right, Aditya? Now from this C, imagine that you are taking a cubical box of 1 meter by 1 meter by 1 meter. Okay. So through this surface per second, so many photons are entering. Okay. So now you have to just calculate that how many photons are present inside this box. Okay. So a photon that enters from here, how much time it takes to come out from this side? From here to here, the time is 1 meter divided by c. Okay. So per second, these many photons are entering that box. So at any instant, how many photons are inside that box? The number of photons which are inside that box will be n into delta t. Understood? So it should be 1.4 into 10 raised power 3 watts per meter square, okay, divided by energy of the photon, which is 3.105 electron volts. That is a number of photons per second which is entering. So the number of photons which are right now inside this are going to be the time taken for a photon to cross this box, which is of height 1 meter. Okay. So that is going to be 1 meter divided by 3 into 10 raised power 8. So this should be the number of photons. Have you understood the calculation, Aditya? So whatever you got in the A part, just divide it by C. You should get the answer for the B part. Is the question clear? Okay. Next, let's come to question number, what was it, 10 in the same chapter, right? Yeah, question number 10. The answer is matching. Roughly you divided by 3 into 10 raised power 8. You're getting that over. No? They've approximated up to first place of decimal. No? Okay, let's look at question 10 next. It says a sphere of radius 1 centimeter is placed in the path. So let's say we have this sphere and it's placed in the path of parallel beam of light which comes out of a large aperture. Okay, so you can visualize the parallel beam of light like this. So it's streams of photons which are incident in this kind of manner. Like this on the sphere of radius r. Okay. Intensity of the light is given to us. Okay. And the radius is 3 centimeters. Now the sphere completely absorbs the radiation. Find the force exerted by the light beam on it. Okay. So this is about momentum of photon. Momentum of a photon is h by lambda. Okay. Now it's not given to us that the light is monochromatic. Okay, but let's start by assuming suppose the light was monochromatic, and with that assumption I'll show you that the final result is independent of whether the light is monochromatic or not. So assuming single wavelength present, suppose we assume single wavelength is present of wavelength lambda, then the momentum of each photon is given by h by lambda. Okay. So any photon absorbed will result in an impulse delta j because of a single photon will be nothing but change in momentum. So that will be h by lambda. Okay, this is that impulse due to a single photon. So now you have to just find out that per unit time, how many photons are incident on this. If n or delta n by delta t is the number of photons, okay, incident per unit time, okay, then the force will just become this number of photons incident per unit time into delta g. Okay, so it will just become delta n by delta t into h by lambda. Clear so far, Aditya? Okay. Now see, if you draw a circle like this of radius r, every photon going through this circle is incident on this sphere's hemispherical surface. Okay. So delta n by delta t is nothing but the number of photons per unit time going through this. So delta n by delta t is nothing but the area of that circle pi r square multiplied with photon flux. That is number of photons per unit area. This is incident from this. So this is nothing but pi r square multiplied with intensity upon hc by lambda. So this is your delta n by delta t. So now you can substitute that here and you can see that your force will just become projected area of the hemisphere, which is pi r square, into photon flux. So that is the number of photons hitting per second into momentum of each photon, which is h by lambda. So interestingly, h by lambda cancels out. So that means if I assume monochromatic light, it is independent of the wavelength. So even if I assume multichromatic light, Okay, and I assume there are different wavelengths, lambda 1, lambda 2, like that present, then I'll have to divide the intensity into sectors, I1, I2, I3 for each wavelength, and calculate the force for each of them, but we'll get a summation. And in that summation, it will be independent of lambda. So finally, the answer will be the same in terms of intensity and area. So you can see it is that projected area pi r square into I by C, h by lambda cancels out. So this will be our force. So here this will become pi into 3 into 10 raised power minus 2 whole square multiplied by the intensity, which will convert to watts per meter square. So 10 raised power 4 in watts per meter square divided by speed of light, which is 3 into 10 raised power 8. So this is the value of the force we should be getting. Okay, so let's see, this is pi into 9 to 0.5 by 3 into 10 raised power minus 4 plus 4 minus 8. So this should be the force in newtons. Oh, my mistake. The radius of the sphere is given as 1 centimeter. So just make a correction here. The radius is 1 centimeter. Okay, so Aditya, I hope the question is clear. This and the previous question, I hope they are clear. Okay. Now the 11th question, which is like a continuation of this. Now that one is much more complex actually, because there you'll have to assume that it's not perfectly absorbing, which means that it can also reflect light. So the moment reflection comes into the picture, you'll have to actually get into an integration. So I'll explain to you how to work that out. But first, let's understand how the momentum transfer happens, or the absorption of momentum by the sphere happens in the case of reflection of light. So in the case of reflection of light, what is happening is that if we consider an incoming photon which is incident like this, okay, at an angular position theta like this. So what will happen is that that particular photon after impact, okay, its velocity will become like this. So here you can see the angle of incidence was theta, this angle of incidence. Okay. So after reflection, the angle of reflection will be equal to theta. Okay. So it will be coming in, making the impact at speed of light, and then after impact it will be going off with speed of light like this. So for a reflected photon, okay, the momentum transfer will be in this sort of direction. The impulse it will apply will be in this sort of direction. Okay. And this incoming momentum is of magnitude h by lambda. The final momentum is also magnitude h by lambda. So the change in momentum will become 2 times h by lambda cos theta. So it is position dependent. So the impulse that a single photon applies when it is incident at an angular position theta is given by this. Okay. So now what we'll have to do is we'll have to consider an entire ring like this. We'll have to consider a ring like this, whose thickness is r d theta. Okay. And whose own radius is r sine theta. So the area of that ring will become 2 pi r into thickness. So 2 pi r square sine theta d theta. So now on that ring, the number of photons incident per unit time, that will become photon flux. Okay. Multiplied with that area's component, which is perpendicular to this. Because see, the ring's thickness is like this. The ring's thickness that we've taken, this r d theta, so if we cut it by a plane like this angle is theta. So the projected area of the ring that is, okay, perpendicular to the beam, perpendicular to the incoming beam, that will become dA cos theta. So that's why there will be this term of cos theta also. Okay. So the number of photons hitting per unit time will be photon flux, which was I divided by hc by lambda into dA cos theta, which becomes 2 pi r square sine theta into cos theta into d theta. Okay. Now, out of this impulse, how much is cancelling and how much is resulting in force in this direction? So you can see the impulse is along this direction. So its cos component is adding, the sine component is cancelling. So dF is going to be this rate at which photons are hitting it into the impulse because of each photon, okay, into a factor of another cos theta. Okay, so the force that is acting just because of a thin ring like this, which is experiencing reflection of photons, that differential force is given by this relation now. Two pi r square sine theta cos theta d theta multiplied by the impulse because of each photon, which has a factor of cos theta, and multiplied by another cos theta term, this one. So you have a cos cube theta sine theta integration kind of term. So you can see that again h by lambda will cancel out, and we'll have 4 pi r square I So this 2 and 2 by c into sine theta cos cube theta d theta. This kind of term we'll have. Okay. So for the net force, we have to integrate this now. This has to be integrated from theta equal to 0 to theta equal to pi by 2. Okay. And from that, you will be able to calculate the force. So you put cos theta as z, so sine theta d theta becomes minus dz. So this will become to the power 4 divided by 4. So we'll have 4 pi r square I by c into minus cos to the power 4 theta by 4 from 0 to pi by 2. So this is a factor of 1 by 4, and that cancels out with this. So this force comes out to be 4 pi r square into I by c into 1 by 4. So pi r square into I by c. Okay. Now see, this is assuming that there is 100% reflection. Whereas earlier, assuming there was 100% absorption, the formula was the same. Now we assume that some percentage of the light incident is absorbed and some percentage of the light incident is reflected. Even then, the total intensity being I, the force will be the same formula, pi r square into I by c. That's why they've said that even if we assume that there isn't 100% absorption, that means some percentage is absorbed and some percentage is reflected, there will be the same amount of force. Okay, so this was a pretty complex application of this momentum transfer and impulse concept, more like a mechanics question like this. This type of question is not going to come in the current pattern of JE because it's a objective paper and not subjective. But for your practice of integration and for your overall understanding of collisions and momentum transfer, this is a good practice, which is why I've shown it to you. There are a few examples in HCV also in the solved examples where they've done calculations of this type. Okay. So make sure you understand this concept of projected area properly over here when we are considering the number of photons incident per unit time, etc. Okay, so I will just leave you with this now and conclude today's session. We have another lecture coming up this week, so I'll pick up the remainder of the doubts in that session. We have finished the photoelectric effect doubts, I think. Next time we'll look at nuclear physics, and there are some questions I also want to discuss. Okay, so that's it for today's session. People, wish you all the best. Area, na? See, if you visualize this ring, it's like a ribbon you've wrapped around the sphere, which is having a curved surface. But the beam of light which is coming, it's coming parallel to the diameter, parallel to the horizontal diameter. So from the angle at which the beam of light is coming, how much is the area of that ring which is projected perpendicular to it? So its thickness is not r d theta then. Okay, its thickness becomes r d theta's vertical projection. So when you work out the angle with the vertical, it will be theta. So the thickness of the ring projected on the vertical plane, okay, to which the beam is perpendicular, that thickness is actually r d theta cos theta. So that's why the projected area becomes dA into cos theta. Okay, good. Okay, so that's it for today, people.